Hello and welcome back to Intro to Computer Networking. My name is David Young and this is part 4 of our series covering the basics of computer networking. In today's video we're going to talk about network performance, the factors which influence how well the network is able to move data between devices. So one important term that we're going to need to define here is bandwidth. Bandwidth is also known as link transmission rate, and it's simply the rate at which a router or other device is able to transmit bits over a certain link, a link being a medium in a way that two routers or other devices are going to be able to connect to each other. And so bandwidth is going to be measured in bits per second because it's how many bits a device can push onto a link every second. And it's represented by the variable r, typically. And different links have different bandwidths. Wi-Fi and 4G cellular, for example, have bandwidths that are going to be in the tens of megabits per second. Whereas certain links like fiber optics and Ethernet cables, notice how physical links tend to be a little bit higher bandwidth. These links have bandwidths in the tens to hundreds of gigabits per second. And so that's an improvement by a factor of 1 to 10,000. And so you'll see that those physical links are going to tend to be better. But what you need to understand is that bandwidth is just how much data can be transmitted every second across a certain link. Now, because bandwidth is limited, and because a lot of people are using the internet, we often end up with a situation where packets arrive faster at a router than they can be transmitted out to the next router. You remember packet switching is just bouncing packets through routers until they reach their destination. So in our example here, you'll see that this link has a bandwidth of 100 megabits per second. And that's going to be an input link on this router. Well, this output link only has a bandwidth of 1.5 megabits per second. And so there's going to be a problem. This data is going to be arriving faster than this router knows what to do with it, than this router can handle it. And it doesn't help that there's a second computer also sending data. And so what's going to happen is that the router is going to hold on to those incoming packets so that it can store them and it can transmit them eventually. And so we call this a queue. It's a queue of packets that are going to be waiting for their transmission over the output link. But you might already notice a problem here, which is that a queue must be finite. It's storing data, so it has to be finite. And what's going to happen when the queue fills up? Well, what's going to happen is packet loss. So we see here in this illustration, the buffer, this is the queue, this is where packets are waiting to be transmitted. Well, this router is not transmitting fast enough, and so this packet which is coming in from B, the router can't do anything with it, and so it's just going to be lost. And so certain protocols, which we talked about in the last video, are going to tell devices if you don't receive a packet, or if you're missing a packet when you try to reassemble at the other end what the data that was sent to you was, you need to tell whoever was sending you that packet that a packet got dropped and they need to retransmit. But some protocols don't do this. So for instance, UDP, which is used to live stream video, does not do this. And so that's why a lot of times if you're watching a live stream, the quality might suddenly degrade. It's because a packet got lost, but it never got retransmitted because you're watching it live. Other protocols, like when you're accessing a web page or YouTube, for example, are going to generally have higher fidelity because they can retransmit packets that get lost in transmission. So there are a few things that we use to analyze network performance, and one of these is going to be delay. And so we calculate delay at each router. And so we call packet delay the time that one packet spends at one router. And packet delay, we can get the formula for packet delay by adding up all of the different delays that are going to happen at that router, or that node, or switch. So the nodal delay, the delay that a packet has at one router, is going to be the processing delay plus the queuing delay plus the transmission delay plus the propagation delay. So let's define each of those terms. The processing delay is just the time for the router to figure out what it's going to do with the packet. So it needs to figure out where it's going to send it and then get it appropriately positioned to be sent on that output link. And it also needs, in some instances, to check the integrity of the packet, that it hasn't lost data or been corrupted somehow. But this processing delay is ultimately very small. It's in microseconds, so to the order of 10 to the negative 6, and sometimes even less than that. The queuing delay is going to be a relatively big source of delay depending on network traffic or how much data is currently sitting in the queue. And so it's the time the packet's going to spend in the router's queue, and this is going to depend in turn on the workload, on how many packets are coming into that router versus that router's ability to put those packets out toward their correct destination. The transmission delay is the time for the router to transmit the packet onto the output link. You'll remember that this is synonymous with bandwidth. And so the transmission rate, or the bandwidth, is going to be a function of the transmission delay is another source of delay, and that's just the total time it takes for the router to transmit all of the information in the packet onto the link. And you'll remember that output links have a certain bandwidth. And so to get the transmission, we just need to figure out how many bits are in the packet. We'll refer to that as L. And then we'll divide that by R, the rate at which the link can output bits. And that'll give us how much time it takes for the router to transmit the packet onto the link. And then the propagation delay is just the time that it takes for the signals to travel from one end of the link to the other. And this is negligible because bits are going to propagate with electric signals or electromagnetic signals at near the speed of light, c, in cables, and at the speed of light in fiber optic cables. And so this is ultimately going to be relatively negligible. One metric that we're going to use to measure the workload for a router is traffic intensity. And traffic intensity is equal to L alpha over R, where alpha is the average number of packets arriving at the router, and L is the average packet length, and R is the output bandwidth. So it's just the average packets arriving at the router times L over R, which is the transmission delay for that average packet. And so this metric of traffic intensity is going to be helpful in determining the average queuing delay at a router. So you'll see here that our traffic intensity, if LA over R is low, that is, if there's a small number of large packets, or perhaps more but smaller packets arriving, and it's a high output bandwidth, we're going to have a relatively low queuing delay because the router is not getting backed up. But as we go towards 1, that queuing delay is going to increase dramatically because more and more bits are coming in, and the router is less able to handle each of those bits. And if we pass 1 right here, our queuing delay is going to become infinite because more bits are going to be coming in than the router can handle, and that stack is just going to keep building and building, that stack of work. This is similar to traffic on a highway. The traffic is going to just build up if there's a lot of it, and it's going to cause a lot of congestion. But if there's not a lot of traffic, then there's not going to be a lot of congestion, and there's not going to be a long queue to get through a certain area. A final useful metric for analyzing network performance is going to be throughput. And throughput is basically the speed of your internet connection to another host. It's the rate at which bits are going to travel from one host to another. That's illustrated here by this line. It's the bit rate between two hosts in a network. Now, throughput's going to be impacted by a lot of factors. I've cleaned up the previous diagram a little bit. But we're going to see that there's delay in here. This is a link, and it's going to have a bandwidth of R sub s bits per second. Then we're going to probably have a queuing delay in this router, and then another transmission delay through this link. And of course, this is a very simplified example. There's probably lots of routers and lots of links, but each of these is going to add a delay, and it's going to slow down our throughput. And the bottleneck link is the link that has the slowest bit rate. And it's going to be the bottleneck for throughput. It's going to be the limiting factor for how much throughput you can get. And a way to think about it is this. If you stood at a waterfall and you were trying to redirect that waterfall, and you just had a little bucket, the amount of water that you could move from that waterfall to wherever you want to go is limited by how much that bucket can move at once. And so if you're trying to catch water from the waterfall that's pouring millions of gallons of water down, and your bucket's 1 gallon, and you can move 1 gallon per second toward where you need to go, your throughput, even though you're connected to this waterfall, is only going to be 1 gallon per second. And so in a similar way, the throughput is harshly limited by the weakest link in the chain of links. Next up, we're going to talk about network security. And that's going to be the final video in our series of Intro to Computer Networking. So I hope you can join us for that. Please feel free to comment, and remember to like and subscribe. Thanks.